Because this is an engineering class and not a technician's class, I want to give a quick theoretical underpinning of what we're doing so it's not completely magical. Let's say you've got this circuit. You've got a voltage source, which is a pure cosine of omega t, and it's connected across a capacitor of C farads. And you're interested in finding the current through it. You can do that without using phasors, using the constitutive equations for a capacitor. And the constitutive equation for a capacitor, remember that's a fancy word that means what's the relationship between current and voltage for the device, is I equals C dV dt. So in this example, it would be C times the derivative of cosine omega t. And you know, to take the derivative of cosine, you take the omega out, and cosine goes into minus sine of omega t. How can we write this as a phasor? We can write it as a phasor by converting it into a cosine waveform. You know, cosine is off from a sine by either plus or minus 90 degrees. Electrical engineering is hard, so of course it's going to be minus. And now let's convert that into a phasor. So it's not exactly equal to it, but I'm going to say we're going to just transform it into a phasor, and that would give us minus C times omega, that's its magnitude, and its angle would be minus 90 degrees. Okay, great. So that would be its I, capital I, as a phasor. A reasonable definition of an impedance is equal to the voltage over the current. And if you convert that voltage source here into a phasor, you can see the voltage source is just 1 at an angle of 0 divided by minus C times omega at a minus 90 degree angle. Oh man, that's a complicated thing to draw, isn't it? And let's simplify that down still further. So, okay, so the numerator is 1. I'm going to write it out with the angle just to make it totally explicit. Minus C omega at an angle of minus 90 degrees. And we talked last class about how you divide two phasors. We said that A at an angle of theta 1 divided by B at an angle of theta 2 is equal to A over B at an angle of theta 1 minus theta 2. So applying that rule here, we get it's equal to 1 over minus C times omega. I'm just going to reverse that to minus omega C. And it's going to be at an angle of 0 minus a negative 90, or an angle of positive 90. A at an angle of 90 degrees. Here's our real part. Here's our imaginary part. We've got 90 degrees up, and we have our A. I want you to see that that is the exact same thing as simply J times A. So I can rewrite this as saying it's equal to or minus J all over omega C. The last part of our proof is to say what is 1 over J. And you can simplify that by multiplying it by J over J. J over J is always going to be 1. But that gives us J in the numerator over J squared in the denominator. And you know J squared is just negative 1. So therefore 1 over J is equal to negative J. And now we can write this entire expression as 1 over J omega C. And that is where we get our 1 over J omega C for a capacitor. Now that you've seen it, you'll never need to do it again. Let's move on to an actual example.